Lab 1 Charged Tape by Thomas Patterson. Introduction. The purpose of this lab is in this lab you will prepare charged pieces of scotch or clear tape. After observing their interactions, you will do an experiment to determine approximately how much excess charge is on one piece of charged clear tape, as stated in the lab instructions. The fundamental principles used in this lab were Newton's second law, the force of gravity near Earth's surface, and Coulomb's law. Computational model used. I produced a computational model in GlowScript of the two charged tapes exerting an electric force on each other and experiencing a gravitational force, and used this model to estimate the amount of charge on each tape necessary to float one tape above the other. Modeled the charges on each tape as a single point charge located in the center of the tape. Assumptions made. Each U-tape, tape A and tape B, has the same net charge evenly distributed along the length of the tape. Treated each tape as if all its charge were located at a single point at the center of the tape. I assumed the normal forces of the erasers on tape B could be ignored, and I assumed that air resistance could be ignored. Preview of results. Manual calculations found that each piece of tape had a charge of about 9.3 times 10 to the negative ninth coulombs. The computational model estimated the amount of charge on each piece of tape to be 9.33809 10 to the negative ninth coulombs. The manual calculations and computational model output answer are very close to one another. Experiment and calculations. I'm not going to go too deep on the details of the experiment as we all did this lab, but this tape here marked with the letter B is our system, and the surroundings include the other piece of tape, which will be referred to as tape A, the erasers that tape B is touching, the earth, which puts a gravitational force on tape B, and the air, which causes air resistance. In this lab, we assume that air resistance and the normal force of the erasers on tape B could be ignored. This is us setting up the lab, and tape A later goes under tape B and causes it to float. The tapes were attracted to a pen with negative induced charge due to rubbing it through hair, so the charge of both tapes is positive. This is a free body diagram of tape B. In the moment it is floating, tape B has an acceleration of 0. When applying this to Newton's second law, this means the net force on the tape is 0, and the tape is in static equilibrium. This means that all the forces acting on the tape cancel each other out to equal 0. When applying the assumptions we made, this means that the magnitude of the electric force of tape A on tape B is equal to the magnitude of the gravitational force on tape B. And here are the calculations. As you can see, we put the mass of tape B into the gravity formula to find the force of gravity acting upon it, and due to the fact that the only other force acting on it is the electric force from tape A and going in the opposite direction, we know the magnitude of these two forces are equal. Then we took Coulomb's law and did some algebra to rewrite it in terms of Q. Since we are assuming both tape A and tape B have the same charge, we can put Q1 and Q2 simply as Q squared, and then isolated Q and plugged in our knowns to find that the charge of both tape A and tape B is 9.3 times 10 to the negative 9 coulombs. Now here's for the coding. The code did not take a whole lot, as we know that the two forces acting upon tape B cancel each other out, so we really didn't even need to include them because we know that they're just going to add up to 0. So we just simply put in the knowns of tape B and a couple of knowns of tape A and plugged it into the modified Coulomb's law we had, where we isolated what charge is to calculate what the charge of tape B and in turn tape A, because we assume they have the same charge, is. And the computational model found that the amount of charge on each tape necessary to float one tape above another is 9.33809 times 10 to the negative 9th coulombs. And now for discussion and conclusions. Similarities and differences. The computational model and manual calculations of the experiment resulted in around the same charge for the pieces of tape. The slight difference is likely due to differences in rounding. This makes sense as the three fundamental principles used for the manual calculations were also applied to the computational model. And the conclusion that both of them came to is that the charge of both tape A and tape B is about 9.3 times 10 to the negative 9th coulombs, and positively charged. Possible sources of error. Any of the assumptions made for this experiment were not true and led to a significant difference in the result. Rewind the video to the assumptions made section for more details. Error in calculations, error in coding, and human error when conducting the experiment. Any of these could result in a possible source of error. What if? If electrons had positive charge and protons had negative, each tape's charge would have the same magnitude but different sign. This would cause the tapes to repel in the same manner as they did in real life. Any charges that repel in real life would still repel in this hypothetical scenario, as while the sign of their charges would be flipped, they would still be like charges and repel. The same goes for charges that attract in real life. Example, two positive charges of 2 coulombs would repel in real life, and then once this hypothetical is applied, they would become two negative charges of negative 2 coulombs, and still repel in the same manner as the two positive charges did in real life. Why? It is important to handle the charged tapes as little as possible, as humans are decent conductors and significantly larger than the tape. Due to this, humans act as a ground and can give electrons to the positively charged tape and cause it to neutralize if the tape is handled too much. This could happen when the tapes come into contact with other objects. Their charge could dissipate. Thank you so much for watching. Have an awesome day.